we go. Okay, so the plan for today, my plan for today is to make it so that we discuss Lecture 2 for the most part. If at the end of Lecture 2 we have some time left over, we can talk if you have any homework questions, but also remember there's office hours and email and all that time for it. So one other side note, if you do come to office hours with homework questions or R questions, or whatever, bring your laptop and I'll work with you to try to get the code working and then try to show you how it works. Or whatever, not just office hours if we have a meeting scheduled. So. Okay, Lecture 2. We're starting with kind of an odd place. So a lot of people just jump in and we start seeing path diagrams and everything like last week. But I want to work with you to go through SEM from a broader perspective, just a slightly broader perspective. And that's kind of the nuts and bolts of what we're getting at. And you saw on the quiz today some of those nuts and bolts. We're talking about distributions. Distributions for data, distributions for latent variables, distributions for error terms, all that. And last week in class you saw a little bit of notation with a distribution. Something was a normally distributed error, and maybe the factor was normally distributed. So all of that is the underpinning of SEM, but all of that is your choice. And I think that's the part that's lacking from a lot of SEM texts. One of the texts, one of the required readings from this class this week was the first chapter of a textbook by Klein. It was his 2002 version of the book. His 2007, or his most recent, the third edition, I don't actually like as much because he's kind of changed some things and I'm not quite happy, so I actually like the second edition better. But that being said, he writes it as if there is only one distribution. There is only one way of doing things, and that's really not the case. In fact, I want you to walk out of here with the understanding that, if you're thinking about using these types of methods for some type of research project, maybe your dissertation, master's, some type of conference presentation, if you're sitting there thinking, well, I was going to use SEM, but maybe I should be using IRT, I don't want you to have to ask those questions. They're the same thing. At some point, the labels stop applying, and what really does apply are the distributions, the assumptions that you make. So we start with distributions. It's a little bit esoteric, a little bit more mathematically statistical, but I'm going to try to keep that to a minimum, just trying to get you to understand what they are, how they work. So, stop me if you have questions. Maybe I should stop. Do you have questions for me? Why are we here? WTF template. I should get up TweetDeck and let it message me if you have anyway. If there was only a way you could submit anonymous questions. I've been in your shoes before, and if you're like me, you're like, oh, if I'm only going to ask a question, I'm probably going to out myself as the one guy who's the slowest in class. And believe me, I want your questions. You're not the slowest. Anyway, we're starting today with things that are heavily jargon. Random variables. Univariate distributions, Gaussian. These are things that hopefully will start to make a little bit more sense by the end of the day. We're starting with the idea of what's one variable, right? One piece of data, one factor, one error, one thing. That's what is a univariate. And then we're going to quickly move from one to many. That's where multivariate distributions come in. But to get to multivariate distributions, and if any of you peeked at the optional readings for this week, I don't know if you. There were chapters assigned from a multivariate textbook. They're all in matrix algebra, linear algebra, and these are something that I just want you to know, to see, and if at any point you see that, to help you unpack it. It's just a shortened way of writing a lot of notation really densely. It doesn't look like that at the beginning. It actually literally looks like a different alphabet altogether, a different language, different writing, and this is kind of what we're doing. It's a different language. So, key questions. We're going to try to do this today. These are some of the questions like we had on the quiz and whatnot. Just try to focus what we're doing. Why is knowledge about randomness variables important to learn to use with SEM? Okay. We're going to hopefully answer that today. What are the two parameters of the univariate normal distribution? What do they govern? Quiz question. Aha. Oh boy, Templin. What are matrices and what basic algebraic operations can be conducted with such things? Oh, when's the last time you thought about algebra? In algebra. When was that for you? I know. It's tough, right? Well, we're going to talk about algebra again. And this is coming from a can I be real for a second? I failed algebra. All right? I failed algebra. I actually failed English, but you can see that. I nearly dropped out of high school. I didn't tell you this before. So I got to college, and I was in remedial college algebra. It didn't count for credit. That was because I needed to try. I was in a community college, and I needed to try to get an associate's degree to transfer to some four-year school. And I walked into my first college class. It was this remedial college algebra, and the professor put on the board a big capital Greek sigma, and I think I lost it. I was just like, oh my God. Like math phobia and everything else. And so I actually took a statistics course because I checked off the math requirement for the associate's degree rather than business calculus, which I figured I couldn't do. And I loved statistics, and all of a sudden I learned all this stuff. So, point being, if it looks like that, if you're like me, that's cool. I get it. I'm not expecting anything more than that. Just work with me, bear with me. You get what you need out of it. That's it. This is not a math class in some respects. It's a statistics class. So I won't ask you to do math. I'll ask you to do data analysis. Anyway, finally, analogously to question 2, what are the two matrices of parameters that govern the multivariate normal distribution? And what do they? What are the two matrices of parameters of the multivariate normal distribution? What do they govern? So at the end of the class, unlike last time, I will pull this slide up and we will answer these questions together, and hopefully that'll give you a little bit better understanding. So, start with the beginning: random variables and distributions. I remember in that basic stats class we sort of started on this stuff, and it sounded, oh, that's so cute that, if we roll it, we always talk about a coin flip or rolling a die or a pair of die, playing craps or something like that. That's a random variable. Well, random variables are key because they provide the distribution of the random variables provide the specifics that accompany our assumptions in our data analysis, right? So we're doing a data analysis because we have a set of research hypotheses. But what drives the data analysis are saying, I assume this about my data, I assume this about my data, I assume this about my data. And if all those assumptions hold, then the answer I get from my analyses is evidence to support or reject it, really. There's really support you can't prove, but you can support the hypothesis or reject it all outright. So if those assumptions are wrong about the data or not matching your data, it's not going to work well. Right? What do I mean? Think of it this way. Let's imagine you go and take something that's a binary variable. You have in your homework gender, 0, 1. What if like that we had something about graduation from high school, status about graduation from high school. People who graduate will give a 1. Actually, we'll flip it. People who didn't graduate will give a 1. People who did give a 0, just for the heck of it, right? You want to predict graduation status, right? Maybe you collect a bunch of out there variables. If you stuck it into a regression analysis, like we have in the homework 1, where you're trying to predict the outcome of it, it's not going to go too well. It's not going to go too well because what's implied by the analysis is that you have error that's some continuum, which really means y itself, the outcome variable, is on a continuum. 0, 1, 1, while they're not really continuous. They're discrete, right? There's no other value. It takes one or it takes the other. That's it. Whereas the continuum, you could have 1.4. That's like someone who's 60% graduated. Right? That would look like me for a good time being. Right? So how do you do that? Anyway, point being, the more you know about the analyses, assumptions that you do, the better you can tailor the analyses to the data you have. And then the more evidence, or the better you can believe the evidence it's giving you about your hypotheses. So that's the big picture, but more precisely than that, once you make these assumptions, it's these distributions that govern almost everything else about the statistic. So for instance, how on earth do we get numbers? Remember in my last example, last week, I had this diagram. We had marital status predicting happiness. And we had a bunch of other lines and variables and whatnot. Where'd those numbers come from, right? Those numbers come from, I use something called maximum likelihood, which we'll talk about next week. But the core of maximum likelihood is something called likelihood that comes from these distributions themselves. So trying to build the distributions to make it work forward. Also, you commonly like to test hypotheses if we're using more frequentist approach to data analysis. So that p-value that you saw last week, we talked about something divided by something else is a z statistic, and it gives us a p-value. The reason why that happens comes from maximum likelihood too. So in my head of putting this together, if I teach you about distributions and how they're interchangeable, you can pick different ones. Everything else that follows from it is pretty much the same. Maximum likelihood works the same, whatever else. And so that question I said when you walk out of here, should I do IRT or SEM? You'll just say, oh, IRT is an assumption that my data have discrete categories. And SEM, well, they don't usually use that assumption. And that's the only difference between the two methodologies. That's it. Crazy, right? So everything else works the same. Maximum likelihood, p-values, everything that you work for can be working the same. The difference is the distribution. So I'd like to teach you the distribution and try to build that from it. Okay. So typically, and if you read along in Rex Klein's book, the chapters I gave you, which are good for the most part, you'll see that he notes that we have normal distributions for everything. Normal being the bell curve, right? I'm going to call it normal. Sometimes you'll hear the word Gaussian, standing for Gauss, mathematician in the 1800s. What's his first name? I thought I heard it. I don't remember his first name. Joe? Bob Gauss. Frederick? I don't know. Johann? I don't know. It's one of these, classical German or something. I don't even know it's from Germany. Maybe from Hungary or Austria. I don't know. Anyway, point being, he used this distribution to describe data. Oh, did I hear this? Carl. That's a good one. Carl's a good one. Anyway. So normal and Gaussian mean the same thing. Typically in statistics, you'll see the word Gaussian more. Normal is our applied statistics. So you'll see Rex Klein says everything has to be normal, or the multiple version counterpart of it, multivariate normal, to do SEM. And that's just not true. Right? We don't need the things to be normal. Anything it's interchangeable. Everything is mix and match. It's like going to Chipotle, and you pick your burrito, you pick your shell, or none, right? All of that. The distributions are the things that you put in your burrito. There. Tweet that. Distributions are burritos. Anyway. So that's what this class is for. So I try to motivate it. I probably go too far on it, but it gets into there's nothing about data today at all. I'm going to keep trying to bring it back to data. Next week we'll get back to data. So what is a random variable? Something that's random means there's at least one part of the outcome, at least in part due to chance, and something that's a variable, right? Something that's value changes. Right? So you put it together, and you've got a variable whose outcome depends at least part on chance. Think of it this way. These are your data. That's the chance, right? If you go out and you collect a happiness inventory, each of the items are the random variables. Right? You can take a look at the items. Maybe you have a Likert scale and 5 points on the items, 1, 2, 3, 4, 5. The value that a person might select is the random variable, right? And they pick it, hopefully, because it relates to their happiness in some way, their value of happiness. So we're going to use little x some of the time. My notation may be inconsistent to denote a random variable today. And a random variable, the outcome of a random variable, gets described with a statistical distribution. Right? This is where we have these nice curves, right? On the left over here, this is a chi-square distribution. So the random variable here is a continuous variable that's positive. Perhaps this is something like income when in high school. Just think of it that way, right? And so the line represents the relative frequency. So if you observe data and this blue line were to fit the test, you'd say, oh, I found a person whose value was like a 2, or how many hours a week did you work in high school? Well, 2, okay, that's really relative to the rest of the people in my data set. That's pretty high, that's pretty frequent. It's not a probability, it's a relative frequency. In fact, the number on the x-axis, that's all it is. It doesn't really do much for us. So, have you heard of chi-square before? I'm assuming you have. Where do you use chi-square? Contingency table? Right? No, you have this 2 by 2 table and you wanted to see if it was a good chance or whether or not things were associated. Remember that? Independent set, vaguely? There was a chi-square involved with that? And it had degrees of freedom. So that's just part of it. So each of the degrees of freedom listed right here, and all chi-square is doing is giving you this shape for the distribution. And so did you look up chi-square? Do we still do chi-square tables in the back of the book? Remember that? Or do we do it like in Excel now or R? I used to like all of these. Remember what we talked about? You had a 2x2 table. Alright, so you got 1 degree of freedom, and you found that your test statistic, you did the observed minus expected squared over expected, and your test statistic was 10.7. Is that significant? How did you tell? Did you look it up in the table? You punched it into a computer, you got p-value. That p-value comes from this distribution. Right? With 1 degree of freedom, it's this yellow line, and it's the probability of being at the tail, the extreme end. It's the probability of being that point or more. And to figure out what that means is really what we have to assume, or what we actually define the distribution as, is that under each one of these curves, the area under the curve has to equal 1. So if you were to say, oh, I'm at 6, what's the probability of being a 6 or higher? You take the area of this part, right? Eventually, if you take a calculus, it's the interval, right? From 6 to infinity. Well, if you take that, that's now a probability. So the distribution helps define a space for probability, it helps define a sample space, and that's it, right? We use chi-square for some things, we use normal for other things, but here's the thought. When it comes to data and it comes to what we do in this class, we have to think about what the distribution of our data could be, right? If you have, I think here, negative. What type of data can we collect that can be negative? Current value of your net worth. I'll tell you mine's negative. All right, how's that? We write, and I'm hoping most of you have more net worth than I do. That's a good thing. But the current value of your net worth can be negative. This is not, chi-square is not a good distribution to use for it. Very simply because it can't be negative. Right? Chi-square is also not a good distribution to use for something that's like binary. 0 and 1 with discrete cases. That's a distribution. Here's another distribution. This is the multivariate normal distribution. We love this one. This one's going to get used to death in this class. Because even though I said SEM can go with any combination, the bulk of this class will be spent on normal and multivariate normal. So if normal, what a multivariate normal is any one dimension here. Here's one variable x, one variable y. You can think of this as maybe height and weight or something like that. And it describes the shape of both of those observations per person. Right? So if you collect for every person in your sample a height and a weight, now you don't just have one random variable, you have a pair. And how they vary and co-vary together is described by this distribution. So it's the height. Right? And so the most likely part is to it. So if you just looked at one of these, like x over here, it's hard to see, x would look like a bell curve. It's pretty good. They're usually really skewed and messy and messy. Yeah. Y would also look like a bell curve. Okay? This is y all by itself. This is x all by itself. These are called marginal distributions. This is the margin of what happens. This is their joint distribution. It's just happening together. How are we doing? So, the thing that tells you the shape, right? So we go back to algebra again. High school. Boy, for me it was college. But, okay. What gives us this shape? It's an equation. So that equation has a name. It's called a probability density for continuum. It talks about how dense probability would be centered in a place. Sometimes it's called a probability mass function. All right, mass typically gets used for a categorical or discrete distribution where you don't have curves, but maybe you have a bar diagram defining it. So that mass, and the word mass actually is an interesting thing. If we were to take the mean, if this was an actual physical quantity, maybe we had a piece of wood that was shaped like that, and we wanted to take its mean, like the mean of a skewed distribution is pulled out towards the tail, so right here, right? That's actually the balance point. of the distribution. Right? Like a moment of it. It's just kind of, you can balance it on its mean. Kind of crazy. So that's where the word mass comes in. It's a physical quantity to it. Okay, so questions. Fascinating. No, not really. I love this stuff, as you can tell, but that's okay. You don't have to. It's not your thing. That's fine. Just get through it. There are different types of distributions. There can be continuous, which you just saw before. Height of a person. Your outcome in a general linear model. Could be discrete. A person's gender, a person's sex, a person's marital status. Then you could have mixtures of continuous and discrete. Right? Right? You could basically say, think of number of cigarettes smoked today. For those of you who might smoke, you might have a continuum for this, or a count at least. Actually, it's a discrete count, but it's countably many, we'd say. There's no upper endpoint to it, but there's some value. For those of you who don't, you're at 0. No, I don't smoke, so it doesn't even apply to me. So some type of mixture of it. So for most of class, we're going to deal with continuous distributions only. That's it. But we will discuss a few discrete things at the end. And maybe if we have time, I'll throw a couple mixtures in. But there was a part of the chapter 1 that I had assigned that Rex talked about M plus and this general version of mixture distribution, whatever, and everything's in SEM, that sort of was saying. It's all distributions that govern it. So, okay. So what do we use model distribution data analysis for? They help us make our assumptions. They are, first question, they help use to describe distributions of data, distributions of parameter values, and distributions of error terms. That was all of the above on number 1. So, way to go, if you got that. They're used almost everywhere. They're even behind the scenes. They're why we describe the word model. If you were in analysis of variance class, you probably never heard the word ANOVA model before. And actually, there was a university I used to work to in a state in the north of which I cannot speak. Megan used to go to school there. They like corn a whole lot. I said ANOVA model once to somebody, and they looked like I was from Mars. It's not a model, it's ANOVA. No, really, there's a model, there's a distribution, there's something that we're doing to describe it. Underneath the hood, this is how it works, right? So, anyway. Big picture, we have to make sure the data follow this distribution, otherwise what you're saying about the data may not be true. Right? That's why we care about it. Seems plausible. So we're going to talk about continuous univariate distributions. And in this sense, I want you just to understand, what's a distribution? Oh, it's this range of things that could happen, or the likelihood of what could happen in our experiment, in our study. Right? The range of height values we could observe and how relatively frequent they happen to be, for instance. So here are 3: a uniform distribution, a normal distribution, and a chi-square. We've seen 2 of those before. But each distribution gets described with a set of parameters. And all the parameters are the things that go into the equation to help you draw it. Right? That chi-square distribution that we saw before, believe it or not, it only has one parameter. It's the number of degrees of freedom. Right? So for each different number of degrees of freedom, we got a different shape to the chi-square. And that's how parameters work. And actually, in statistics, what we're doing with our models is we're plugging in values that are data-based for our parameters to get a shape of a distribution that mirrors our data the best. That's the thought. It's kind of the abstract part to all of it. So everything we're going to do in SEM in this class, every model that we do, we have this equation, or we have this linear type model to it. The result of that shows up somewhere in a distribution, and it governs something about the shape of our data. So it's kind of cool in that respect. But anyway, all 3 of I picked 3 out of that. You can pick any number of parameters. And as a matter of fact, plug for a course in the fall, if you're really into distributions and how we do data with more than just normal, I'm teaching a course that tries to do that in the fall. It's called Generalized Linear Mixed Models. It's essentially what happens when we have count data, what happens when we have categorical data, what happens when it's continuous. But they're not normal, right? Mixtures, all that. But we're just going to focus on normal, and I want you to know the big picture of what a distribution is. Okay. Here is a uniform distribution. It's a box. What? All right. So basically says there's two parameters, an A, which is the lower limit, and a B, which is the upper limit. It says, hey, you have a random variable, an outcome, and you can observe it within a range. Right? I'm trying to think of a good random variable in a uniform interval. Have you ever used a random number generator on your calculator before? Pulls out a digit between 0 and 1? That's useless distribution. Any possible fraction or decimal value is possible between 0 and 1. That's a uniform distribution. Anyone's possible, but the key thing about the uniform is they are all uniformly likely to occur. No single one happens anymore, and that's what you see by this y-axis. The probability density function is flat. And so it makes this really easy to work with. We don't even need calculus. We can deal with area with a rectangle. Right? We can say, what's the probability that someone is at or above this value right here? Well, the area under that curve, we know the height given by our function, and we know the distance. We can figure out length times width, or length times height, and figure out that area. It's a probability. So you'll see the area under this has to be 1 under that same idea, right? What's the width of this is b minus a, right? That's your width. So the height has to be 1 over b minus a. So you multiply width times height to get the area, you get 1. So it's a distribution. So if you thought things could be, what happens? Well, that distribution function, that height, the PDF, that's important to us. That is actually the nuts and bolts of what drives maximum likelihood. And it's actually what gives us all the inferences we want to see. And it's just ridiculously simple in some level. Oh, I plug in a value and I get a number that's the height. That's it. So here, with the uniform distribution, here's some just example values. You can pick any x. It doesn't matter. Here are the top two, the likelihood or the how high a value of x happens to be for 0.5 or 0.75. When a and b are the same, they have the same height. They're uniformly likely. The only thing that changes is the height of the curve if a and b change. Right? So it's kind of a, in some respects, very limited distribution. We don't see it very often. We don't do anything with statistics for it, except for simulation studies. Some of you are doing simulation studies for your project. This is what's driving your simulation. By the way, helps get you around IRB. IRB does not need to approve fake data. Go figure. So that distribution, that's our distribution. And it has parameters A and B. If I were to ask you where you thought the mean would be, what do you think? Right here in the middle, right? There's nothing that would balance it halfway, half above and half below. And that's what it happens to be, 1/2 the distance from A to B. The variance of it, I put this up here just because it's kind of funny. You can create you can calculate a variance of a theoretical distribution. There's there's ways of doing that I'm not going to describe to you, but it's 1 over 12 times b minus a squared. And what I always like to see when I see that 12, doesn't 12 seem pretty arbitrary? I only put like 13 there. Like, or just like you do statistics long enough, you see a number in a formula and it's like 7. I don't know. All right. Let's get fun here. This is the one that you'll love, the normal distribution. You've seen the bell curve, but have you seen the function that gives you it? I have a tattoo of this. I just want you to think I'm that crazy that it might happen. That's nuts, right? Oh, don't talk to Templin. He's crazy. This is the normal distribution. This ugly-looking function, right? Let me try to unpack it for you. That's your data, x. The mean of the distribution is mu. That's one of the parameters that governs it. The other parameter that governs it is sigma squared. That's the variance of the distribution. So if you were to say, I have this normal distribution for my data, I know the mean is 0 and the variance is 1, you'll draw a curve that will tell you the relative likelihood of your data compared to everything else in that map. So this pi character right here, that actually is the constant pi 3.14. You can put as many digits as you like. It's 1 over the square root of 2 pi sigma squared times E, which is another constant. EXP stands for a constant 2.71. Is that Euler's number? Is that the right word for it? EULER? Someone can help me with that. Megan's sort of nodding. I don't remember. I ask this every time I teach it, and I can never remember it. So it tells you what's important. Anyway, that's the letter E, or 2.71, raised the power of what's in this exponent. Okay? Now, if you remember algebra, exponents get unexponentiated by logs. Right? And so, 2 things about that. Remember in your homework, you had to look for the log likelihood? When we take the log of this thing, the exponent goes away, and all we're left with is the determined size. It actually turns out to be, even though it's really ugly to look at in the picture form, working with it mathematically is a lot easier than other distributions because that E disappears. But here's a few examples of a normal distribution. These are distributions where you are pretending that you know the mean and you know the variance. And in fact, all of today, we're going to pretend we know the mean and we know the variance. What happens if you don't know the mean and know the variance? Next week. We actually flip it on its head. Oh, we know data? Let's go solve for the mean and solve for the variance. That's the flip. Right? Now here we know the mean, we know the variance, we just don't know what data can happen. So let's go with the red line. I like that. That's why I'm wearing this red shirt. Mean of 0, variance of 1, that's here in the middle. This is something we call, it holds a very special place, called the standard normal distribution. Standard because if you take the z-score, right, the mean is 0, your variance is 1. Do that here. Anyway, what this shows is the mean of this is the most likely value. It's at the peak, right, relative to the other value. The value it happens to be is roughly 0.4. That value means nothing right now. That is not the probability of observing the mean. It's the relative frequency of which it occurs. Right? As you can see, under the distribution, the blue distribution here, that has a variance of 0.2, a smaller variance. It's much more narrow of a width, much more peak. So the relative likelihood of that mean is like 0.9. Right? So one way or the other, you wouldn't compare across distributions. It just happens to be that. Let's see, what else? So mean itself governs the location, or where the center point happens to be. I just picked out the 2 zeros. There's a third 0 here. This green one has a different mean, because its peak is at a different spot. So its mean is -2. That's its location. So the mean is one of the 2 parameters of the normal distribution. It governs the location. The other parameter is the variance. And what does it govern? The shape, right? The width. Anything roughly in that, I'm going to grade pretty leniently. So if you're close to that, I'm happy. Right? So here, these 3 distributions right in the middle have the same mean. They all have different variances. One is very peak. That means most of the data is concentrated in this region right here between -1 and 1. One is very flat. It means data are likely to be more spread out. So how does it relate to your data? Well, when we make these assumptions, we may have distributions for our parameters. And we'll figure out where they are based on the assumptions. Trying to get you out here. How are we doing? Is it warm in here to you too? No? Yeah? Yeah, okay. I was going to say. I know I'm normally sweaty when I teach, but today feels... Anyway, it's warm outside. So here's some examples. What I want you to learn about this class, a distribution exists, and it has a height. And how do we get a height? We plug in the data and then the parameters. Okay? So the top 2 values of data, these are 2 values of data that come from a normal distribution with a mean 0, variance 1. Once you plug that into that ugly formula, I can remember it, 1 over square root of 2 pi sigma squared times e to the x minus mu squared over 2 sigma squared. Right? That one? Simple, right? But you plug that in, or you plug it into the R function d norm, and it will give you how tall the curve is. And actually, that's how you plot these. all there is to it. But so, for instance, if you were to say, here's a question for you, and this is where we're going next week, is maximum likelihood, where we get our numbers from. Here's a value of 0.5. It comes from a distribution with a mean of 0, a standard deviation or a variance of 1, so the height of that curve is 0.352. Right? Here's another value of 0.5, so like we observed the same data. Right? If we pretended that we always observed the data, and we didn't observe the mean or the variance, could you pick which distribution was more likely to give you the mean or the variance between these two? Just on the exam? The answer is yes. Comes with height. With height for likelihood. So if you say, I observed a 0.5, I have no idea the mean, I have no idea the variance, and here are my two options, you pick the one with the bigger number. Oh, 0.5 is more likely to come from this distribution, mean of 0, variance of 1, than this distribution, mean of 0, variance of 5. It's kind of weird to think about, but that's where we get our numbers. Right? We assume a distribution, we figure out its parameters, they give us heights, and then we go and try to search for what those parameters might be based on their heights. Got it? So far? Cool. If you can get that part, we're awesome. If you can't get that part, come talk to me, we'll still be awesome. You're still awesome. This doesn't govern your awesomeness. But in terms of why I'm teaching you this. So here, this is chi-square. Right? So I may remember the normal distribution because I had to write it down enough. I have to look up this one. Right? This is how like the order of difficulty gets tougher and tougher and tougher. This thing right here is a chi-square distribution. That drew the first graph we saw today. This little thing that looks like a Z, I think that's the Greek letter nu. That thing is the degrees of freedom. And all this happens to do is to say, okay, I observed a number that happened to be 2.7. You plug 2.7 in for x, you say, oh, I had 5 degrees of freedom, that goes for nu. And you calculate the rest of all this, including this ugly gamma function, which I don't give you, thankfully. It's an ugly integral. And it will give you the height of the curve. But here's the thing. Under a chi-square distribution, the same thing goes. If I said, oh, I've got 2.7, is it more likely to come from a chi-square with 3 degrees of freedom or 5 degrees of freedom? The height's the one that tells you the best. Bless you. So, where I'm going with this is even though you'll read, like you said, Red and Klein finds that you have to have multivariate normal. I said that's not true. If you wanted to, you could do SEM with the chi-square distribution. Say, oh, my data aren't normal. They're chi-square. They're like median income or something like that I collected. That's totally cool. You can do it. The computer may not want you to do it, but you can conceptually come up with it. Cool? Oh, boy. So there's a bit different value. Actually, here, let's just do that. I have a degrees of freedom of 3. What's the most likely, I have a value of 3. X equals 3. What's the most likely distribution this came from? The one with the biggest curve. The red one. With the degrees of freedom of 4. That's maximum likelihood for you, actually. That's where the foundation starts. Okay. Let's take a break. Stop here. Take a break. We're going to get to joint distributions in just a bit. That's going to take your patience. So get up, take a mental break, get some cool air. Thank you.